let's consider a problem to demonstrate some of the properties of floor functions. So this is from the Mathtrix monthly issue regarding floor functions, and the problem reads, find the number of ordered pairs x, y of non-negative real numbers that satisfy the system of simultaneous equations, the floor of x plus y is equal to 10.1, and x plus the floor of y is equal to 10.2. So right off the bat, this problem kind of resembles the classic system of equations problem, but there's a slight twist, obviously, with the presence of floor functions. So we had to remember a few key ideas about floor functions in solving this problem. Now, obviously, you can just try plugging in numbers and see where you get, but obviously that method is not highly accurate and it could take a long time. So we're going to use the definition of floor functions to solve this. Previously, I had defined floor functions using words, but we can do the same thing with algebra. So let us do that right now. This is the floor function defined algebraically. Now, what is it really saying? Well, what is this symbol, first of all? Because we haven't defined that yet. So these brackets around x refer to the fractional or rational part of x. Now, what does that mean? So let's consider one of our examples, 2.1. If we found the fractional part of 2.1, or the rational part of 2.1, it would be 0.1. So basically, it's the non-integer part of 2.1, right? For 3.1, it would be 0.1 still. For 3.2, it would be 0.2. So anything after the decimal point, anything that's not an integer. Now, obviously, we already have the definition of a floor function, and x is just x. So how does this true? Well, if you think about it, if we have the 2.1 example again, let's say x is equal to 2.1. Well, you have the rational part of x is 0.1 plus the integer part of x, which is 2, and obviously these two are equal. So that's basically the definition we're going to use to solve this problem. Now, let's replace, or substitute rather, x in the problem and y in the problem for the following equation. So the first equation would become the floor of x, which we keep, and now we're going to write y in terms of this. Now, when you're writing y in terms of this equation, you're just basically substituting y in for x. So this is going to be equal to the floor of y plus the fractional part of y. Now I just flipped these around a bit from the original definition, but I'm sure you guys can tell. And this is equal to 10.1. And for the second one, when we substitute an x, or this side of the equation for x, we get, and again, I'm switching this a little bit around so that it is easier for us as we continue on. Now, we continue. These two new equations that we have reveal some interesting things. Because for one thing, we know that the floor of x plus the floor of y must be an integer, because the floor of x is an integer and the floor of y is an integer. And two integers added together, it's not going to become a fraction, right? It's going to remain an integer. So basically, that's what we know about these two. Now the fractional part, we know something else as well. We know that the fractional part of x and y both of them cannot be greater than 1. Because if, let's say the fractional part of x is greater than 1, then it wouldn't be a fractional part, right? Because there would still be an integer left in it. It would have come out. By definition, the fractional part must be less than 1. Now, since the fractional part must be less than 1, we know that the floor of x plus the floor of y must equal to 10. Because think about it. The largest this fractional part could possibly be would be like 0.99999 all the way until infinity. But even then, the floor of x plus y, the floor of x plus the floor of y, will still have to be equal to 10 in order for this problem to actually come out to 10.1, right? Because if it was equal to 9 and you added that fractional part, it wouldn't even reach 10. So we know that the integer sum of these two must be equal to 10. Now, because we know the integer sum must be equal to 10, we know that the fractional part of y must be equal to 0.1, and the fractional part of x must be equal to 0.2. So let's keep that in mind as we continue on here. And now this is just a consequence of simple plugging in right? The floor of x plus the floor of y is equal to 10, 10.1 minus 10 is equal to 0.1, and similar situation here. Now let's continue the problem. Remember what it's actually asking us. It's asking us for the ordered pairs of x and y, right? So let's imagine that a, the variable a, is equal to the floor of x, and b is equal to the floor of y. Now we have that a plus b must be equal to 10. And in essence, we're finding all the integer pairs a, b such that they add up to 10, and by doing so, we will find all the integer pairs of x and y that add up to 10 that satisfy this equation. So let's just take a systematic approach in solving this. We can write the following order of pairs a, b such that they satisfy a plus b is equal to 10. We have 0, 10, 1, 9, 2, 8, 3, 7, 4, 6, and 5, 5. Now, obviously the reverse of all these would also work. So we can write 10, 0, 9, 1, 8, 2, 7, 3, 6, 4, and the opposite of 5, the switch order of 5, 5 would be the same thing. So in total there are 11. There are 11 ordered pairs. Now, because we know that there's a correspondence, a direct bijection correspondence between the number of pairs of a, b, and the number of pairs of x, y, we know that the total number of pairs that satisfy the original equations has to be 11. And there we go. That would be our answer. Now, if we wanted to actually write out all the pairs of x, y that satisfy the equation, we would simply attach the fractional part of x to the integer part of x and the fractional part of y to the integer part of y to get x, y. And as we remember, the fractional part of x was equal to 0.2, and the fractional part of y was equal to 0.1. And just by adding them to the following pairs correspondingly, we would get the answers. And that's basically it for this problem.